Thank you everyone for joining me for this video. I am Mr. Ish. We're looking here at a good comparison video. Washers versus cylindrical shells with regards to volumes that are generated when curves are rotated around a line of axis or a line of rotation. Very quickly, look here at this top diagram. We have a single function. If you look at the area below that curve and you rotate it around the x-axis, what you end up getting is a good rotational solid. If you take a cross section of this solid, you have a disk pop up, and you know we've seen this before. The first solid can be analyzed in terms of its volume using both the disk and the cylindrical shell technique. Now look here at this lower side. We have two functions over here, and now we end up having an area between curves. Here we have an area below the curve with regards to an axis. Here we have an area between curves with regards to both functions. We have something here which looks like a quadratic parabola and a radical. The area between that curve, if you were to rotate it, you end up getting a solid which is like this. Contrast it to the one here on the top. The one on the top is through and through solid. There's no open space or empty space in it. When you look at this solid right here, you actually have an open funnel shaped space inside it because of all of this region which is empty. Especially when you're rotating it, all of this region over here is empty, and that leads to an open space. When you do a cross section of this is why you end up getting washers. The disc and the washer are different. The disc is through and through solid. The washer has a little bit of a donut shaped empty space in it. But this type of configuration can be handled in terms of volume determination by both washer and cylindrical shell technique. What it tells you is that the cylindrical shell technique is much more versatile and more universal than either the disc and the washer technique. In this video, our question will be a comparison of the washer and the cylindrical shell technique in terms of volume determination of the resulting solid for something which looks like this, an f function and a g function. It will give a good function over here. And when you look at the washer technique, you know you're looking from your line of axis, which here will be your x-axis because our line of rotation will be our x-axis. When you're looking up, the first function you hit, and when you're looking up, the second function you hit. The first function you hit will give rise to an inner radius. The second one will give rise to an outer radius. And the inner radius here, you know, will be easily determined, and then it'll go and feed into a formula. Because we know the cross-sectional slices for both discs and washers are always circular, you'll always feed it into a circular area formula, and then that'll give you rise to an inner area and an outer area. And you know for the washer technique, when you're doing the volume determination, you could easily push the pi out as a coefficient, and then you're looking from a lower limit, A, we'll call this A, and the upper limit along an x-axis dimension, and you'll be doing the outer area minus the inner area, and the net effect of that cumulative area integrated over your interval. These washers developing from the lower limit to the upper limit, their cumulative effect in terms of their summation gives you a good volume determination. And you know you've seen something like this before, and it's not hard. The same representation here with the solid arising from this with regards to cylindrical shell technique is slightly more complicated. We've seen the formula for the cylindrical shell technique, and I've shown you that in the previous video with regards to x or y, it doesn't matter. From A to B, we have something which comes here in terms of a length, something here in terms of a height and a width. I'm not putting a dx or dy because that is representative of this w that you're seeing here. When you take a cylindrical shell and you have seen this, you cut it and you expand it and you flatten it out, you have a rectangular prism. This rectangular prism has a length, it has a width component, and there's a height. Think about it, volume of prisms and cubes is always length times width times height. Length times width times height. Here the length, as you know, ends up being the circumference of an opened cylindrical shell, 2 pi r. The height was exactly your function f of x, or we can also give it a different designation which we'll talk about momentarily, and width over here was your thickness, which could either have been dx or dy. Hence the formula is exactly the way it is. Let's look at this height component that needs to be addressed. When you're talking about areas between curves, let's look at something like this. You have something here which looks like a right boundary curve and a left boundary curve. In another instance, you could have something which looks like this, a function which looks like this. Here you have a top boundary curve, and here you have a lower boundary curve. This very well is your height. If you are looking at something like this and you have rectangles which are drawn in a horizontal manner, you know you're going to have the height from one end of the rectangle to the other end. In this instance, you can have a xr minus XL being representative of your height. In this instance, you're having a rectangle, a Riemann rectangle drawn vertically, so you can have a top boundary and a lower boundary, and that difference gives you the length of that or the height of that, and that would be YT minus YB. In each of these cases, you have to remember here the equation is in the x equals format. Here it's y equals format. So this very well is easily determined when you think about it in this form. In this specific instance, look, we have our line of rotation as x-axis. We have something which looks like this. Your rectangles have to be always parallel to your line of axis or your line of rotation. My line of rotation here is the x-axis. My rectangle must be parallel to that x-axis, so it has to be horizontally oriented. I will look up in a perpendicular manner to that rectangle, and that will give me my radius, which will be my y. For the same representation, if I were doing a rotation around a vertical line of axis, which is y-axis, and I've told you the Riemann rectangles must be drawn. Remember, the Riemann rectangles are what give rise to these cylindrical shells by their rotational effect. The Riemann rectangles are always drawn parallel to your line of rotation or axis. If the line of rotation is y-axis, now my rectangles must be in a vertically oriented manner, and I must look across perpendicular to the rectangle to get my radius. Here I'm looking at an x-word movement, and therefore my radius will employ an x value. Here this will become a 2 pi y, and I'll end up integrating with respect to dy. In this instance, it'll become 2 pi x. We're looking here at the circumference component right over here, and I'll end up having an integration with respect to dx. Hence, you see the flip phenomenon that we've talked about. So you must keep this in mind. Your rectangles are parallel to your line of rotation, but you look across in a perpendicular manner to determine your radius. Now, with that background in place and our historical knowledge of these rotational dynamics and the volume determinations, let's look at our first example using the washer technique. And you know, washer technique comes into play because you have a region of space over here. A cross-sectional slice will always be a washer, and washer always has a circular cross-sectional dimension to it. Our functions are x squared, root x, interval 0 to 1, and rotation about the x-axis. You know, here the lower curve must be my x squared, and the top curve is my radical or my root x. We have an interval 0 to 1, and you can easily determine these points. This right here will be 1 comma 0, this will be 1 comma 1, this right here will be 0 comma 1. It's very easy to plug in these and get your x and y coordinate pairs. Easy. How do we go about doing this? Well, you know, when you're looking up to the first curve, you're having an inner radius. The inner radius here is going to be x squared. When you're looking from that line of axis or rotation to the next curve, you have an outer radius, and that ends up being root x. Everything feeds into the area formula for a circle. The inner area here and the area outer, this becomes a pi x to the 4 because you're squaring the radius. Here you're squaring it, you'll get a pi x. You know, it's always the outer area minus the inner area, the difference, the net effect integrated across. So volume with respect to x here, as is always the case for the washer and the disk method, you're not doing any flips over here in terms of your intuitive thinking. It's along the x-axis with the horizontal line of rotation. Everything will be with regards to x. We can bring the pi out. We have an interval along the x-axis 0 to 1, and we're integrating in the x dimension. The outer area, we have isolated the pi, so we're just left with an x. Minus x to the 4 and dx. Easy polynomial integration here. X becomes an x squared over 2. We have a pi sitting out. X to the 4 becomes x to the 5 over 5 using the template technique for polynomials. X to the n plus 1 divided by n plus 1. From a 1 to a 0, 0 is meaningless. You essentially have for your volume 1 over 2 minus 1 over 5. You can easily calculate this, and you'll end up getting 3 pi over 10 as the volume of this rotational solid that I showed you before, looking something like this. In both instances, our examples will have the same rotational solid develop, and it will be a rotational solid, except in this instance the rotational solid, as I said before, is open, but it's closed here, and you have a rotation around this spinning top right here. That's our volume here, 3 pi over 10. When we use the same question here with the cylindrical shell technique, we must arrive at the same answer. Let's look at this technique here. Cylindrical shell, exactly for the same parameters, 0 to 1, x squared root x, and rotation about the x-axis. You know, my rotation is x-axis. My Riemann rectangles, which I would draw, that would rotate and give rise to those cylindrical shells, must be parallel to that line of rotation. My line of rotation is horizontal, therefore my rectangles would be horizontal as well. I would look across in a perpendicular manner to determine my radius, and since I'm moving upwards, my radius here must be of y values. When I'm looking at the extent of this rectangle, I need to determine its height. and I have a right boundary curve and I have a left boundary curve. The difference of that two ends will give me my height. But here we have to convert these things into x equals format. Y equals x squared, y equals root x. Y equals x squared is really the same thing as root y. Y equals root x is the same thing as y squared, and here we have it, root y minus y squared, and that is my height. The height here is not a single item, but it ends up being an expression because we're looking here at a region between curves. Next thing we need to look at is the circumference, which is 2 pi r, except here r is y, so it's 2 pi y. Our volume formula will be, as you know, we can push the 2 pi out as a coefficient. We look at intervals here along the vertical dimension y from 0 up to 1. We have a y over here, and then we have root y minus y squared dy. Volume with respect to y, you have a 2 pi, let's open up the parentheses, y times y to the 1 over 2 is y to the 3 over 2, and then y cubed and dy. We have to integrate this, and it is not hard. The integration of that will come down right over here. Y to the 3 over 2 will become y to the 5 over 2 over 5 over 2. Remember, n plus 1 divided by n plus 1. Y cubed will be y to the 4 over 4 from an upper 1 to 0. You can flip this fraction around here. You'll get 2 over 5 y to the 5 over 2 minus y to the 4 over 4 from an upper 1 and 0. 0 meaningless. You are looking only at now 2 over 5 minus 1 over 4. You know a common denominator here will be a 20, and you have a 2 pi sitting outside. 5 goes in 20, 4 goes in 20, you do the adjustments over here, you'll end up getting 3 over here. You end up getting 6 pi over 20, which is the same thing as 3 pi over 10, which is the volume that we were looking for all along. So you should get the same value with regards to washers and cylindrical shells, or discs and cylindrical shells. There should be no difference in their net result or the final result, only the difference lies in the procedure. And there's a lot more to the cylindrical shell technique that we need to look at. I'm not even telling you why you would utilize this over the other techniques. We're just introducing you to this technique and showing you how it is a universal and a versatile technique. But you have these various techniques at your disposal. Just keep in mind you can use this technique for more instances than you can use the other two. And that is something we will talk about in another video. Thank you for watching. Have a nice day.